This will be our last lesson on the periodic table, and we're going to continue with the periodic trends that we talked about the other day. The learning goal is the same thing you've seen throughout. Most importantly, you want to know that the periodic table is arranged in a certain way, and because it's arranged, you can predict properties of elements based on their location on the periodic table. The other day we talked about the atomic radius, and we also talked about ionization energy. And what I want to make sure that you are extremely comfortable with are those periodic trends that we talked about the other day. So we're going to build upon the table that we started the other day, and what you're going to see there is, for example, if this box represents your periodic table, as you go across a period from left to right, you get an increase in the effective nuclear charge. That means the valence electrons are drawn more tightly to the nucleus, and as a result, what happens to the atomic radius as you go across a period?
It gets smaller.
It gets smaller. And that's because with the increase in effective nuclear charge, the valence electrons are drawn more tightly to the nucleus. Now, with the valence electrons being drawn more tightly to the nucleus, what happens to the ionization energy? It increases. Now, ionization energy is what?
It's the amount of energy it takes to strip the electron.
You got it. It's the energy required to strip a valence electron, an electron, from the outermost shell. So with the increase in effective nuclear charge, what happens is the radius of the atom decreases, the energy required to strip an electron from the outermost shell increases. Now, as you go down a group, you know that the valence electrons are placed in higher principal energy levels farther from the nucleus. So you have an increase in the shell number, that is an increase where the valence electron is. You also have an increase in electron shielding. We talked about this the other day as you go down a group. And as a result, what happens to the atomic radius? It increases, is correct. And the ionization energy decreases because as those valence electrons are in higher principal energy levels farther from the nucleus with more electron shielding, it takes less energy to strip an electron from the outermost shell. So if you understand the reasons, you will be able to make any prediction about a property of an element in this regard. So what we're going to talk about first today is electron affinity. Now, what does it mean to have an affinity towards something?
You like it.
I just had a question.
Okay.
Above the electron shielding, what does the N mean again?
The N is the shell in which the valence electron is located. So as you go down a group, the valence electrons will be in higher principal energy levels or shells farther from the nucleus. Okay, so affinity means a liking to something.
I thought that E shielding meant like that, like if it has more, then it means more energy is required to strip it.
No. With the increase in electron shielding, what's going to happen there, and I'm just flipping back to a picture. with the increase in electron shielding, that's what you're going to see, for example, with beryllium versus calcium. They both have 2 valence electrons. This is in the second shell, this is in the fourth shell. So as the valence electrons get farther from the nucleus, they experience more electron shielding because there are more core electrons in lower principal energy levels comparing here versus here. So this takes less energy to strip away because it's farther from the nucleus with more electron shielding. The radius is larger. Okay, so electron affinity. Affinity means a liking towards something. So electron affinity is the next trend we're going to examine. Electron affinity is the energy change that's associated with adding an electron to a gaseous atom. For example, let's say that you were talking about fluorine. Fluorine has 9 electrons, electron config 1s2, 2s2, 2p5. Electron affinity is the energy associated with attracting and holding an electron. You're going to make an ion with a negative charge. Attracting and holding an electron. The ion now has gained 1 electron, and it's going to have 2 plus 6 is that octet of electrons in the outermost shell. The energy associated with this process to attract and hold an electron is known as electron affinity. The trend is very similar to ionization energy. One thing I want to make clear is that you are attracting and holding an electron you didn't have previously. That's important. Now, electron affinity typically is going to be negative in regard to the energy value. I'm not really going to go into that this year. It'll be too tricky for you. Here's your trend. It says electron affinity increases across a period. What happens to the effective nuclear charge across a period? It increases. So you're getting more and more positive charge because you have more and more protons. If you want to attract and hold an electron which is negative, which element is going to have an easier job of that? Something with little positive charge or something with a lot of positive charge across a period? More positive charge. So what happens across the period from left to right is as you go across a period, you have an increase in the effective nuclear charge. And as a result, you're going to see an increase in the electron affinity. Electrons are negative. As you go across the period, you have a greater and greater effective nuclear charge, more plus, and as a result, the ability to attract and hold an electron increases. As you go down a group, the valence electron would be added to a higher principal energy level, and there would be more electron shielding. So what's going to happen to electron affinity as you go down a group? It's going to decrease because you're attracting it farther from the nucleus and there's more electron shielding by the core electrons. Electron affinity trend looks like ionization energy, but the meaning differs. With ionization energy, that's the energy required to strip an electron from the outermost shell. With electron affinity, that is the energy associated with the atom's ability to attract and hold an electron. And that's what's indicated here. So across a period, the attraction of charge increases with the greater effective nuclear charge. So the ability to attract and hold an electron is greater. There are some anomalies. I'm not going to go into the anomalies because I think it's too tricky at the honors level. Down a group, the ability to attract and hold the electron decreases for the reasons we mentioned. So let's take a look. Which of the following has a smaller electron affinity? Nitrogen or fluorine? Let's take a look at the periodic table. Nitrogen or fluorine? Smaller electron affinity. Here's nitrogen. Here's fluorine. So nitrogen will have a smaller electron affinity because it has a smaller effective nuclear charge. The energy associated with nitrogen's ability to attract and hold an electron would be less. So let's take a look there. And let's take a look at what a solid answer will look like. So what we've got here is nitrogen has a smaller electron affinity, abbreviated EA, compared to fluorine because nitrogen's effective nuclear charge is less. So its ability to attract and hold an electron, as well as the energy associated with the process, is lower. So elements that are to the left of elements that are to the right, further to the left in a period, you're going to see a smaller electron affinity because the effective nuclear charge is lower. Less energy is required to attract and hold an electron. And when you answer these questions, make sure you answer the question, make sure you explain why, and make sure you define that property. Let's take a look at the next one. It says rubidium or tellurium. Is that what you have in your notes? All right, change strontium to tellurium. Change strontium to tellurium. Let's compare rubidium and tellurium, Te. Let's make that one change. So we're comparing rubidium, period 5, group 1, with tellurium, which has the smaller electron affinity. It's going to be rubidium because it has the smaller effective nuclear charge. As a result, less energy is associated with rubidium's ability to attract and hold an electron. So very similar to what you saw previously. All right, let's look at what happens when you're in the same group. Strontium or tellurium. We want to know which has the lower. Strontium or tellurium. First of all, what happens to electron affinity as you go down? It gets smaller. So which has the smaller one? Tellurium. And let's look at why tellurium has a smaller electron affinity. To which shell would tellurium be trying to attract and hold the electron?
5.
The 5th shell. And what about sulfur? To the 3rd shell. Which element illustrates more electron shielding? Tellurium. So what you're going to have here is that tellurium is going to have a smaller electron affinity compared to sulfur, and that's because it would be attracting and holding an electron to the 5th shell, which is farther from the nucleus with more electron shielding compared to sulfur, which would be trying to attract and hold the electron to the 3rd shell. So make sure you answer the question, When you're going down a group, your reasoning is twofold. So be very careful there. Your reasoning is twofold down a group. You're looking at the shell to which the electron is being attracted and held, as well as the electron shielding. And make sure you explain what electron affinity is. So tellurium has a smaller electron affinity compared to sulfur because tellurium would be attracting and holding an electron to the fifth shell farther from the nucleus with more electron shielding than sulfur, which would be looking to attract and hold an electron to the third shell. Now on your quiz and on your test as well, if I ever ask you to explain, make sure the elements are either in the same group or the same period. If they're not, you've selected the wrong element. If I were to ask a diagonal, and I might ask one on the test, not on the quiz, it's just a multiple choice type question. For example here, which of the following has a smaller electron affinity, selenium or iodine? So we've got selenium here, iodine here, and I would agree with you in regard to selenium. Right, on the diagonal, typically what you're looking for with electron affinity or ionization energy, the greater the number of valence electrons, typically the greater ionization energy or electron affinity. So electron affinity is the energy associated with the atom's ability to attract and hold an electron it did not have previously. Those are the main trends that I will ask you to explain. Primarily what you're going to see. And again, due to the increase in the effective nuclear charge, you'll get a decrease in the atom's radius, an increase in ionization energy and electron affinity. Down a group, due to the shell in which the valence electron is located or where the electron will be attracted and held, as well as the increase in electron shielding, you get an increase in the radius, a decrease in ionization energy, as well as electron affinity. The other trends I'm going to mention here we'll go through. I won't ask you to explain these off, but you do want to feel comfortable with these trends, and you will see some additional problems that you should solve over the weekend in your classwork. The next trend I'll mention briefly is electronegativity. I mention it because it shows a trend. We're going to come back to electronegativity in quite some detail in Chapter 6. Electronegativity is the tendency of an atom to attract bonding electrons to itself when it's bonded with another atom. And of course, when you read definitions, they're pretty much meaningless. They don't make any sense. If, for example, you had hydrogen covalently bonded to chlorine, and you'll learn how to draw compounds in Chapter 6. Oh, it's fun. I promise it'll be fun. Then you get to construct the compounds with little molecular model kits. It's like making puppy dogs. It's fun. You just haven't done it right yet. This is a covalent bond. A covalent bond is when you have electrons that are shared between two atoms, as opposed to an ionic bond in which electrons are transferred from one atom to another. We'll be looking at ionic compounds next week. In a covalent compound where you have a covalent bond, you have electrons shared between the two atoms. Sometimes they're shared equally. For example, if you had two hydrogens bonded together, the electrons in that bond would be shared equally. But sometimes the electrons in this bond are not shared equally. One atom draws the electrons more to it than the other. It's like a tug of war between these two. Nobody really wins, but chlorine is definitely leading the whole way. Electronegativity is the ability of a bonded atom to draw bonding electrons toward it. And the trend for electronegativity is exactly what you see for electron affinity. So for example here, if we were to continue adding trends to our little periodic table here, what you're going to find with electronegativity is that it increases across a period and decreases down a group or family. So that shows the same trend that you saw previously. Same trend that you saw previously. And then the last trend that I want to mention is the metallic nature or the reactivity. We're going to look at both metals reactivity and non-metals reactivity. So let's take a look there. Before we go through and really read, I want you to try and figure out what you have. If you know where metals are located on the periodic table, you'll be very successful with this type of analysis. So what we're looking at here is a periodic table, obviously. Are the metals on the left side or the right side? Left side. Most elements on the periodic table are metals. So you've got metals, as we've talked about. You've got metalloids, not iodine, right there. And you have nonmetals. Okay? Now, what would you predict happens to the metallic nature of elements as you go from left to right across a period? Jared? Yeah, so you're going from left to right across a period. Would you say the metallic nature increases or decreases? Decreases, because you're going from metals to nonmetals. Metals tend to lose electrons, nonmetals tend to gain electrons. Metals typically have 3 or fewer valence electrons. There are a few with 4 or 5. Nonmetals typically have 5 or more, sometimes 4. So as you go across a period, the metallic nature decreases. Now when you look at all of the trends shown here, they all behave oppositely. Also, think now when we showed the video about group 1 elements and dropping them into water. Which element produced a better explosion? Francium is going to be the most explosive when dropped into water. So as you go down the group or family, the metallic nature increases. So the metallic nature increases down a group. Let's think about why. All the elements in group 1 have how many valence electrons? 1. Now, when you compare that valence electron, let's compare, for example, lithium and cesium. Whose valence electron is farther from the nucleus with more electron shielding? Cesium's. And as a result, as you go down the group or family, the metal reactivity gets higher and higher. Metals tend to lose their valence electrons, and this one's valence electron is the farthest from the nucleus with the most electron shielding. It's the easiest to be removed. So as you go down the group, the metal reactivity increases. As you go across a period, it decreases. So if this element is the most reactive metal on the periodic table, looking at your nonmetals and keeping in mind these are of extremely low reactivity, which nonmetal here is most likely to be the most reactive? Fluorine is correct, because keep in mind that nonmetals will gain electrons. They're going to form anions, and fluorine's got 7 valence electrons in the second shell. Which element is more apt to gain an electron? Fluorine or iodine? Fluorine, because you're gaining it to which shell? The second, closer to the nucleus with less electron shielding. So you've already predicted your trends because you understand the reasoning behind it. Metallic nature decreases as you go across a period. Metallic nature and reactivity increase down a group. Which would be more metallic, magnesium or phosphorus? Say it again. Magnesium or phosphorus, what would be more metallic? Magnesium or phosphorus? Definitely magnesium. And then the other question was, which is more metallic, magnesium or barium? Barium, for the reasons that we've already talked about. So you've already done that, and we said nonmetals have the reverse trend, with fluorine being the most reactive nonmetal. So let's just take a minute to throw that property onto our table as well, so we've got it. There is a question in your classwork on reactivity, and again, follow the trend. So for example, as you go across the periodic table, what happens with metallic reactivity? It decreases. So your metallic reactivity, I need another pen. Let's say MR for metallic reactivity. And as you go across a period, what happens to the metallic reactivity? Decreases. As you go down a group, it increases. You've got it. And there are all your trends. There are some trends in melting and boiling points. Typically across a period, they will increase. We're not really going to get into that at this stage of the game. What you want to be comfortable with are these periodic trends. You've got to be able to explain, and I think you will be very successful with all of it. Your explanation across a period, with an increase in the effective nuclear charge, what happens to those valence electrons? They get drawn to the nucleus more tightly, so the radius shrinks, the ionization energy increases, electron affinity increases. As you go down a group, the valence electrons are farther and farther from the nucleus with more shielding, so the radius goes up, ionization energy and electron affinity go down. Question? You do want to indicate what shell the valence electrons are located in, and that will always correspond with your period number. Okay, so what you've got, hopefully, is that you realize that the periodic table is not just a collection of elements, but rather there's a specific way in which it's put together, and because of this, you can make predictions about different properties of elements. Questions?